Singh, and this is my third physics lab related to black hole physics. And so the purpose of this lab is to understand the practical application of physics principles by analyzing the motion of an object in the frame of the force of gravity and circular motion with respect to a black hole. It seeks to validate the fundamental physics concepts of the net force and the impact of circular forces on the trajectory of an object. And so the foundation of this experiment relies on 5 equations. The net force sum, so the sum of the perpendicular forces plus the perpendicular momentum plus the parallel momentum, or the perpendicular force plus the parallel force. Then F net equals dp over dt, so similar idea over here, but the net force is equivalent to the change in momentum over the change in time over the small intervals. And then just the position update formula, so RF equals RI plus V average delta t. And then the force of gravity, which is gmm over r squared times r hat. And then finally the velocity update formula. So a brief preview of the results. We found that the black hole mass was 1.62 times 10 to the 34 kilograms, and then the total net force was 9.6 times 10 to 28 newtons, and then with its two broken down perpendicular and parallel net forces, and then the ship speed ended up being around negative 5.4 times 10 to the 7 meters per second in the x direction, and then 4 times 10 to the 6 meters per second in the y direction. And so now I'll walk through the code. So we had to change the delta t to 60 times 24, which is 86,400, as our interval, because each data point was like a day apart. And then the star's mass is 2 times 10 to the 30. And so as we iterate over the data values, we can find the dp dt. And so in this case, we're starting at index 1, incrementing that for however long the data set is. And then the initial velocity will just be the previous index's velocity, and then final will just be the current index's velocity. So we can use that information to figure out the initial momentum, which is mass times velocity. So we can take this for the momentum of the star. We can just do start at m, so the mass of the star times the initial velocity. That's the initial momentum, and then the final momentum would be the mass of the star times the final velocity. And so we can use that to move forward, delta v, delta p, just changing the velocity, changing momentum, then that over delta t, and then we can figure out the relation with F net. So F net equals dp dt, as we established earlier. And so then we can then find the parallel and perpendicular components of dp dt, which will then help us find the F net perpendicular. Once we do all of that, it'll print a bunch of values that indicate the mass of the black hole. And so the mass of the black hole was found using the F equals gmm over r squared. We just reorganized that for the m to be the focus, which I'll show in the program real quick. But yeah, so we get a bunch of different mass values up here. All I did was average them out and then get that final value. And then to find that mass, all I did was I went to the bottom to print where it's being printed out, and I entered that equation to find the mass of the black hole, which is right here. So the mass of the black hole is the magnitude of F net times star and then over gm. But yeah, the part 2 wasn't as complicated as part 1, fairly simple. All I had to do was figure out the distance between the black hole to the planet and then the ship, and then find the forces on each, respectively. And then use these updated forces to then find the updated velocity and updated position for both the ship and the planet. And then once you run the program, we can then guess and check the velocity to figure out if we can get a trajectory similar to this, where it gets pretty close and then it exits the orbit of the black hole, or the gravitational pull. This earlier, the results 1.62 times 10 to 34 kilograms for the mass, and then there are some errors that have been present just in terms of like the delta t and how close together the intervals were for time, but otherwise it seemed pretty straightforward. Same thing with the ship speed, negative 5.4 times 10 to the 7, and then 4 times 10 to the 6 meters per second. So similar errors, just the difference in time. The delta t could have been smaller to reduce the number of errors. But what does it mean is more important. So based on the above equation, F net equals dp over dt. So the momentum and the net force are fairly equivalent mathematically. But in terms of calculations, while both are easier to describe in qualitative terms, like we could describe the motion visually, Quantifying momentum is much simpler because it all takes is mass and velocity, and a couple other components as opposed to gravity, which requires a much harder tools like the mass of the actual object and stuff. So there was an attempt for entering the orbit, which I can show in a second. Probably mean decreasing the x velocity, increasing the y velocity a little bit, just so that it can not doesn't leave right as soon as it gets into the orbit, but just hovers around for a little bit.